Good morning and welcome to the second edition of Online MATLAB. All right, so today our topic is going to be vectors and matrices. MATLAB has vectors and matrices really at the heart of all the way that it operates because that's essentially how everything is represented in the MATLAB platform. Because of that, I think it's important that we make sure we understand how vectors and matrices work. The goal of this section is not necessarily to make sure that you are excellent at calculating vectors and matrices. That's really the purpose of a math class. But what we're aiming at here today is to get a background in understanding what it is that they do so that you'll know which one is appropriate to use at which time, and also to make sure that we understand all of the associated syntaxes and so forth, and all the great things that are already built into MATLAB to help you work with vectors and matrices. All right, with that, then let us go on over to the PowerPoint. Oh, yes, this is my dog Max, who is Max. There he is. Who's saying good morning to you. Yes, we're down in living. All right, here, let me share my screen with you. Share screen. Oh, there's that. And here's our lecture. Feel free to follow along. The slides are posted on Moodle, or you can just follow along with the video. It's up to you. All right, so this is the lecture for April 1st. This is an overview of what we're going to discuss today. Vectors and matrices overview, vectors and matrices as function arguments. So one of the great things about MATLAB is that you can in fact pass an entire vector and matrix right into functions and it will operate on the whole thing, which makes loop writing a lot less necessary than it would be in some other programming languages which don't do this. Scalar and array operations as they work on vectors and matrices. We'll review all of the math words in case you're maybe a little rusty, but basically a scalar is like multiplying by a constant. Logical vectors, that's things that work with true and false. And finally, we'll talk about matrix multiplication, which I've used as a kind of a broad term for actual matrix multiplication and some other related mathematical concepts such as the dot product. So I've given you a link to a nice video that I found on YouTube. So MATLAB actually has a channel on YouTube where they broadcast a number of the videos that have been put together. They also have some on their website, and I think some of them do overlap. So I would definitely encourage you to take advantage of all of the great recordings that they already have on many of these topics. Some of them are maybe a little bit beyond where we're at right now. So, but do be aware that they have these things here and certainly do take a look at it. All right, so MATLAB at its heart really is a matrix approach of representing things. And part of why this is so important is because it can then take advantage of, well, nowadays, the GPU architecture, how things are actually processed, because when they are represented in that format, then they are able to be processed faster. Of course, MATLAB has been around for a lot longer than GPUs have, and so they've always represented things in this idea of vector representation or matrix representation, because it is really an extremely efficient way to represent a lot of different kinds of data, especially since they're focusing on scientific applications. Many things in scientific applications really lend themselves to be put into a data format that can be represented in a matrix. Suppose you have multiple replicates of an experiment, or maybe you have some number of different things that you want to look at. So that oftentimes is an excellent way to represent it. And that's their strategy. So everything in MATLAB is written to work with vectors and matrices because of their philosophy on how to tackle this problem. MATLAB, in fact, actually stands for Matrix Laboratory. We should learn matrix operations, which are going to allow you to vectorize your code. That means it will run faster. That's part of why MATLAB is so efficient and why it works so well on very large data sets. It is an industry standard for its these kinds of programs. Python is used to some extent. So if you do Python and you learn about NumPy and Matplotlib, perhaps these days Seaborn, you will learn how to do many of the same things in there. That's sort of like the open platform version of MATLAB that's grown up after MATLAB had already been started. So MATLAB's been around. I mean, I first was introduced to MATLAB when I was in college, so it's been around for quite some time. Python, of course, is a much newer language, and the applications that they have are, of course, quite a lot newer as well. Scalars are a special case of vectors. Vectors are special cases of matrices. So let's just remind ourselves what all of these different things are. And so I've got this nice little diagram here to help us remember. So a scalar is a single number, and it's basically a constant. It's usually going to be an integer or some number, but it's a single entity. And then when we have a vector, we can think of a vector as having multiple numbers in it. So it has multiple fields. Could it be a vector of strings? Absolutely, it could be. But usually we're talking about the type of some kind of numeric data. And then a matrix then is going to be a representation of data that's going to be multidimensional. Here is shown a two-dimensional entity here, right? So we have rows and columns. So for example, you might have time series data, right? So you could have like time 1, 2, and 3, and then you could have your different experiments along those lines. Maybe it represents, you know, geothermal data, or who knows what it's going to represent, all different things that you could do. But many things could be cast into these kinds of frameworks, and that's exactly what we're going to be trying to do with MATLAB. I'll mention that we don't need to stop at two-dimensional arrays in MATLAB, but we could also use a higher dimensional one as well. Also, generally, we talk about vectors and matrices as a more general, is a kind in a general idea. We kind of talk about them using the word array to mean that it could be either a vector or a matrix. So we should recognize the fact that a vector is a special case of a matrix. Sometimes we may use the word matrix, or sometimes we may use the word array, which may also mean a matrix, but that a vector is a special case of it and therefore is implicitly included. So a vector is in fact actually a matrix that has only one row. So then let's learn how we could actually create row vectors in MATLAB. So there's a couple of different ways you could do this, but the most direct is to use an assignment statement with the desired elements in it. The square brackets are going to indicate the matrix data type. So notice that, however, MATLAB does not display them when showing the value of the matrix variable. That is, when you press return, that's not going to show. So if we just look down here, we see a little example of some data being entered into a matrix. So into a vector. So this is going to be called V for vector, and we use these square brackets to indicate the type and that it's going to be a vector. And then we have the data 1, 2, 3, 4 separated by a white space. And then when we press enter, it will show us back 1, 2, 3, 4, but notice that the square brackets are not shown. Okay, so then this gives us what our syntax is. It has a variable name here, and then we have each of the elements. We're not restricted to 4, we can have any number of elements desired. The colon operator is really useful when working with matrices. It's used to iterate through a range of integers, so this is extremely useful if you have something that's going to be equally spaced. The lower and upper bound are going to be included when you specify. So here's an example of specifying a range. We're going to go from 2 up to 6, and see this colon, then what it does is it generates the matrix, generates the vector entries with equal spacing between them. So say, for example, you wanted to make a graph, right? You might want to put in some values for the x-axis, and that's probably going to be evenly spaced. Who wants to type all of those out, right? So instead of doing that, we could just use this colon notation to generate all of the x-axis values in the range of interest. So this can be used to generate a vector when the elements are consecutive integers. Notice that the square brackets are not used in this notation. So you give the lower and the upper bound, and again, those are in fact actually included in what you'll get out. We also have the Linspace operator. This stands for linearly spaced. And this is going to create evenly spaced data points between the lower and upper bounds. The number of data points is by default 100. So basically what it's going to do is you're going to tell how many points you want. So say you want data between some certain numbers, and then it's going to give you those data points and make them linearly spaced within that range. The number of data points can, however, be specified if 100 isn't what you want. So similar to the colon operator, Linspace is automatically going to generate a vector across a range of numbers. Unlike the colon operator, it's not limited to working with integers, which should be fairly obvious because the division of the range you give it may not be integers. So what you're going to do is specify the lower and the upper and the number of data points desired. It's inclusive of the lower and upper bounds. So here is our syntax. We do linspace, then you give a lower value and you give an upper value and the number of points. So here, for example, what we're going to do is we're going to linearly space numbers between 3 and 15 with 5 data points. So here we have 3, 6, 9, 12, and 15, right? And here's another example here, running from 0 to 5. We see that these intervals come out to not be integer values, but instead are floats. So basically, between these two operators, you can specify a series of numbers without actually having to calculate it yourself, which is really useful, and also not having to type it yourself. So it depends whether you know what you want your spacing to be, in which case you would want to use the colon operator, or if you want to have a specific number of data points between a particular range, in which case you want to use your linear space operator. We also have other spacings. So there are other ways that the data points could be organized besides linearly spaced. They could be spaced by a log. So this creates a logarithmically spaced sequence of powers of 10. It's important to note that this is actually operating in powers of 10, so it's not just data between different things. It's going to do powers of 10. So what you're going to do is you're going to specify the exponents x and y. So the range is going to run from 10 to the x to 10 to the y. Specify the lower and upper bounds for the exponents inclusive. So again, the x and the y will be included, and the desired number of points that you want. By default, if you don't tell it, it will do 50. So here we do the keyword log space, and then you give your lower power and the upper power and the number of points that you want. So here is an example of generating some logs. So recall that anything to the 0 power is 1, right? So here you see that what we're getting is we're getting these numbers running from 1 to 1 times 10 to the 5th, which is 100,000. We also have the indexing operator. So the index operator looks up characters in a string. This is similar to something that Python will do. The index operator is the round brackets, which is not like Python because Python uses the square brackets. The specified index must be within range of the vector. So for example, if we have vector and then we give an index, it will pull that out. So here is a vector, and I replicated that up here for you, and what I've done is I've shown the indexing underneath. If we do vector of 1, it will give us back 1. Notice that if you are familiar with doing this in Python, that the Python index begins at 0, but in MATLAB it begins with 1. Array indices must be positive integers or logical values. So here we're going to do v of 22, which is going to exceed the number of array elements, so you will get a note about that. There's also the opportunity to slice a vector by range. This is going to allow you to pull an element out of a vector within this specified range what you can do is assign the slice to a new variable, and then you might want to use that variable for something after. We're going to use the round brackets with the colon to indicate a range of elements to select. And again, it's going to be inclusive. So here's our syntax: variable, you give the vector name, and then you give lower, range, and upper. So it looks like this. Here's the vector. Notice I've used the semicolon here to suppress the printing on the next line. Then we're going to say vnew equals vector of the slice from 1 to 3, and then vnew is going to be 1, 3, 17, so it's taken positions 1 to 3 inclusive. We can also slice the vector by specific indices. So what we're going to do here is pull out elements of a vector by specifying the indices of the desired element. These are going to be expressed using the brackets. The elements do not need to be in order or contiguous. The vector containing the indices is called the index vector. So you can think of this as putting into a vector the position numbers of the elements that you want to pull out. So you imagine that you had some data. Think of it as representing maybe even like an Excel spreadsheet. So suppose you read an Excel spreadsheet into a matrix in MATLAB. And then what you wanted to do is you wanted to multiply column 9 by column 15 for some reason. So instead of having to go in and do that every time, what you might want to do is you might want to make an index vector that points to column 9 and column 15. So then instead of specifying that every time, you can just use that as the pointers that will pull out those columns to do your multiplication and whatever else you may need to do with them. So this is what it looks like. You have a variable equals the vector name, and then you're going to have element X, element Y, blah, 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 all the way up to however many that you need. So here's an example. Here's a vector, and here's an index 2, 4, 7, and 8. So that will pull out the second element, the fourth element, 1, 2, 3, 4, 24, the seventh element, so that's the 13, and the eighth element. So you see that they're not even in order, and it's still able to pull them out. You have the ability to mutate elements that are in the vector. What this means is that once the vector is in existence, you may wish to change what that value is. You can access a particular element in a vector using the name of the vector and the index in parentheses, and then assign a new value. So that changing the value is called mutation. If an index that does not yet exist is specified, the vector is going to extend it to create that entry. If a new element has a gap between itself and the last existing element, then the gap in the vector is going to be filled in with zeros. So let's take a look at what's happening here. We would have the vector name, and then we would give it an index, and then we would assign it a new value. So here's the vector, and we say we want to change position 1 to 10. So you see that the rest of the vector remains unchanged, but this position here, position 1, has now become 10. So suppose you want to expand a vector by creating an index. That's what we were mentioning when we give an index that is not in existence. So here, for example, we can extend a vector by a single entry. So we can do vector of 4 equals 4. So here, what we've done is we've added on another position. But suppose we did vector at position 10 equals 10, and we're working with the same vector. Well, position 10 is way down here. So instead of adding just at the next position, it's way out. There's all these interim ones. So what it does is it's going to expand the vector to be large enough to accommodate the position that you've specified and fill in the rest of it with zeros. So that brings us then to column vectors. We've talked about row vectors, but we can also have vectors in columns. So we can create a column vector by entering the elements separated out by a semicolon. So in MATLAB, the semicolon is going to indicate the start of the next row. This is pretty much a theme that's going to recur throughout the use of MATLAB. We'll see it again today when we talk about how to make matrices. The column vector is the same, is the special case of a matrix having only one column. So you see what we're doing here is we have C equals 1, 2, 3, and 4, right? And so then when C reports it back, it comes out as the column instead of the row version of it. You can think of the colon as basically being a return. We can also generate a column vector using transpose. So if you've taken linear algebra, you might remember that transposing a vector means basically rotating that vector by 90 degrees. The colon operator cannot be used to directly create a column vector. However, a row vector can be created, followed by a transpose, which will result in the column vector. So transposition causes columns to become rows and rows to become columns. So if you did a transposition and you transposed it again, you'll first start with a row and then you'll get a column and you'll go back to a row. In math, transpose is usually designated by the superscript T. In MATLAB, it's the apostrophe or the single quote. So here is a row vector. So here we've created a vector using the colon operator. And so now C is going to be equal to R prime, that is the transpose of it. And so we've taken a row vector and created a column vector out of it. Very useful because you don't have to keep typing the semicolon in between. This little diagram up here is showing you how transposition works mathematically. So then, how about creating matrices? A matrix is going to be a generalization of row and column vectors. So why stop at only having one row or one column? You could have more. So let's do that. Enter a row as a vector followed by a colon, and then to delineate the start of the next row, we're going to type the next data. Right? So here we have a matrix where we have 1, 2, 3, colon, 4, 5, 6. So then this will have 2 rows, just like this. It's very similar to when we made our vector that had the row version of it. So when we did that, we just used the colon to basically act as a return. So we're doing a very similar thing here. Matrices have dimensions m by n, where m is the number of rows and n is the number of columns. And a square matrix has the same number of rows as columns and is referred to as an n by n matrix. This will show up because there are some special n by n matrices that may be of interest to you. The number of entries for each row must remain the same. So you can't have 1, 2, 3, and then just 4, 5, and omit the 6, right? It has to fill out the whole thing. So there are a number of familiar operators that can be used on matrices. So here are some iterators, that is that colon notation, which can be used to create the rows of a matrix. So here is a matrix being generated using the iterator. So here we have the colon 1 to 3 and 4 to 6. So this generates the matrix that we just looked at without explicitly typing the whole thing. Not too much of a problem for a matrix of this size, but suppose your matrix was much larger. This can be extremely helpful. Separate rows can be entered with enter instead of the use of the semicolon. So here is an example of typing this in using return or enter in between each line. And that works out to exactly what you would expect. We can use rand to generate random numbers and to fill the matrix with that. So this is going to be used to generate a square matrix. So here we're going to have rand of 3, so that's going to make a 3 by 3 matrix with random numbers in there. The random numbers are going to range from 0 to 1. Rand can also be used to generate an m by n matrix by passing 2 arguments. So here what we're doing is we're specifying 2, 3, a 2 by 3 matrix. So that will give us this matrix down here. Again, the numbers are going to range from 0 to 1. A matrix of random integers can be generated by passing the range and the dimensions. So here is an example of how to do that. So see, we're going to use rand I for integer, 10 to 30. So we're asking for numbers between the range of 10 and 30, and we're looking for a 2 by 3 matrix. So here is what that looks like. Notice that your range needs to be specified in the square brackets. Here we're going to look at functions to create special matrices. So there are some special matrices that you may recognize if you've taken linear algebra. These mainly pertain to zeros and ones. So zeros is going to create a matrix with all elements equal to 0. So here's zeros of 5, and it will create the n by n matrix of dimension 5 by 5, all full of zeros. Ones is going to create a matrix with all elements equal to 1. This is the identity matrix of size 3. We can also pass a single argument, which will create a square matrix, whereas passing 2 arguments will create an m by n matrix. So that's very similar to what we just saw with the random number generation. So we can also do the same thing with zeros and ones. So here, looking at these, we see that instead of creating the n by n matrix, we've specified some dimensions. In this case, 3 by 5, and in this case, 4 by 2. We can slice matrix elements. So similar to vectors, matrices can be selected and or modified using selection ranges. The indicated subscripts must point to an element. So if you point outside the matrix by choosing an entry that doesn't exist, you're going to get a problem. To capture the matrix slice, what you're going to do is set a variable equal to the doubly subscripted slice. The slice range must indicate the rows as the first entry and the columns as the second. So here's an example of what we can do. New matrix equals some big matrix that we want to slice a piece out of, and then we're going to give the row range and the column range. So here's an example of how this might work. Here we're setting up a matrix, again using our iterators. Here it is, and then we're going to select a subset. So we're going to take these slices indicated here, 1 to 2 and 2 to 3, and the subset is going to be 2, 3, 5, 6, which we can see is up here in the big one right here, just like that. Just like vectors, we can also mutate the elements of a matrix. So similar to vectors, matrices can be selected and or modified using the selection ranges. The indicated subscripts have to point to a particular element. Again, if it's outside of that, then it's not going to be any good. You'll get an error. Mutating the matrix is going to modify the existing matrix by overwriting it. The slice range must indicate rows as the first entry and columns as the second. We always say rows, then columns. We do that consistently. So if we use this colon operator, this is going to indicate all values. So if we do matrix of colon comma 2, that's going to say take all the rows and column 2. We use equal to assign the new values. So this is how it would look. It would look like this matrix, and then you're going to have a row range, a column range, and then give you row values and column values. So these will be the new ones that will replace what's over here. Of course, the size is going to have some limitations. So the dimension of the replacement entries must be at least as large as the selection that you've made. So matrix mutation. Here are some examples. So here we're going to set up a matrix. This is a 5 by 5 matrix of 1. Here is another one over here. Okay, so one matrix. So now we're mutating it. We're saying that we want to mutate position 2, 4, and we want to mutate that to 2. So we've taken the second row and the fourth position, 1, 2, 3, 4, and we've reassigned that position to be equal to 2. So that's mutating a particular position. What if you wanted to mutate a whole row? So here we have, again, our matrix. And now what we're going to do is we're going to make the mutation on that. So we're going to mutate 3, colon. Okay, so that means that we're going to take row 3, and the colon means that it's going to be all values. So then when we go into row 3, 1, 2, 3 right here, right, then all columns in there are going to be matched up to new values. And so we've specified some new values here that we're going to substitute in. There we have that matrix getting updated with the new information. So This is just a little diagram to show a little bit about how you can build up matrices. You can do this by concatenating matrices together. And so this is how you could build it up. And so we have this little diagram here with some little blocks to help us just understand that. So you can make matrices just like we can make vectors, which we've already mentioned and we've already seen. So you can do things element by element to make some piece. So here is, say, like a block piece. And then what we can do is we can concatenate vectors or matrices, which is going to then put them all together. So here are some blocks, A, B, and C. And so notice that these are rows, whereas this is a column vector. Okay, so this is what we're saying about the dimensions matter, because there are certain pieces that aren't going to fit together, right? So here we are going to have A and B, and we're going to put those two together. And here we have D and C, which we're going to put together. And then we can take these and put all of the pieces in together to make this pattern just like this. Dimensions, the length function returns the number of elements in a vector. For a matrix, it's going to return the number of rows or the number of columns, whichever is greater. So the syntax is length and then the vector or matrix of interest. The size function is going to return both the number of rows and the number of columns in a vector or matrix. So if you do size, you get back both. Notice that the size function returns two values and that both of these values can be captured in independent variables. So for example, we could do syntax and you have a variable 1 and variable 2 equals the size matrix. So we have some examples of working this out over here. Here is a matrix, and if we ask for the length of the matrix, we get 3 because 3 wide. The size is 2 by 3. And here we have an example of basically doing what we were saying over here, capturing multiple variables into by just one thing. So size will return 2 things, and you can capture each of those into variables. So here we see that exemplified because we have R, C, 2 variables that are going to be catching whatever size returns. So size is able to return 2 things. So R will be equal to 2 and C will be equal to 3. NumL is going to tell you the number of elements. So the built-in NumL function will return the total number of elements in a vector or matrix. For vectors, the value returned is going to be equal to the length because that's how many items are in there. So we just do NumL and then we give the matrix. So here's some examples of this in action. Here's our matrix, and what we're going to do is ask how many elements are in the matrix, and it gives us 9. Here we have a vector, which we've made again using the iterator, and then we ask how many elements are in here, which is 5. And we can also ask for the length of the vector, which would also be 5 because it is a vector and all elements are in the row. And as an expression and not a function, we use it to reference the last index. We can use this with vectors or with matrices. So here is a vector, and if we ask for the last element by using vector of end, we get 5. Here's another example using a matrix. We have the matrix here, and we ask for the end, and the answer will be 9. So notice that it's the rightmost and bottommost element that you'll get back. It's also useful to have an illustration of the matrix continuous indexing in MATLAB. So there will be some examples where the continuous indexing is going to be used. So what we have here is showing you how the continuous indexing is lined up. So in this case, the continuous indexing is going to use the first column, and then it will move into the next one. So it goes down, which may not be exactly what you would expect. So this is useful when we are going to reshape matrices, because the reshaping is going to make use of that numbering that we just talked about. So resizing a matrix means taking something and putting it in, so of some dimensions, and putting it into something else. So back when you were learning your multiplication tables, you might have learned For example, there are some things multiplied together to give the same dimensions, right? So if you have 12 elements, how could you arrange them? Well, you could arrange them in one column vector of 12. You could arrange them in one row vector of 12, or you could do 2 by 6 or 6 by 2 or 3 by 4 or 4 by 3. So all of those different dimensions then could be used based on the total number of data points that you have. And so if you have any one of those matrices, any of those dimensions, you could cast it into a matrix of different dimensions. And the way that it's going to iterate through is that it's going to go, just like we said here, going down the columns first. And so that's how it organizes it. So this is what we mean by iterates column-wise. This is going to return the reshaped matrix, but it does not store the original variable. So if we reshape, then we're going to just give the name of the matrix, the row, and the number of, and the column. Sorry, it looks like a parentheses got cut off here. So what we have here then is a matrix. So this one I've given it is a 3 by 4 matrix. So if we reshape this to 2 by 6, we use the reshape command. We say we want to use mate4, which is what I defined over here. And then when we see what it looks like, we see that the shape of it has changed. So notice that I have this set up so that this is numbering column-wise, and you see that that is retained so you can follow how it's been placed into the new matrix. So here's another example. We could reshape it as a 12 by 1, which then becomes a column vector. And so then we could also reshape it into a row vector. So this is very useful to be able to just reshape automatically. We can also flip a matrix. So flip LR for flip left right flips a matrix with respect to the left and right. So here's an example, and I put in these dotted lines to help you see the symmetry in these matrices. So syntax flip LR is going to flip left to right. It will go between these two, and flip up down is going to flip a matrix with respect to up and down, right? So this is like rotation about the x-axis, rotation about the y-axis is shown here, and rotation about the x-axis is shown here. If you've taken a graphing class, or maybe you encountered this in a pre-calculus class, you can do similar operations on graphs, so you might be familiar with the idea of that from there. This is just really nice to be able to rearrange your matrices this way. And so this just is showing you what the syntaxes are, which are pretty much as expected. And we have a couple of examples shown here. You can also rotate a matrix by 90 degrees, which I've shown graphically with this block representing a matrix. And I put a star on there so we can keep track of where something is, so we can see what's happening. So this is an example of a matrix rotation. If you've done linear algebra, you've probably actually done vectors and matrices. Actually, either one, you've probably encountered rotations. So to rotate a matrix by 90 degrees, that is basically this. So here we have a matrix, which I've generated using those random numbers. And this is going to be a 5 by 3 matrix. Remember, rand gives you a number between 0 and 1. And then we rotate that matrix by 90 degrees. And so we can follow that the items have moved by 90 degrees. And notice the dimensions have also switched. So we started off by having 3. So there are 3 columns. So now there are going to be 3 rows. And the 3 numbers that are up here are now going to be these 3 numbers that are appearing over here. So it's just like following this rotating around. And the same is true for the other side. We can also replicate a matrix. So I've just gotten some pictures of lattices here to help you think about what that might look like in 3 dimensions and in 2 dimensions. So if you have some element and then you want to replicate that through space, that's essentially what this is going to do. So it's going to replicate a larger matrix that consists of an m by n matrix copy of that matrix. So repmat is the replicate matrix, and then you give the small matrix this unit cell. You may be familiar with that term from X-ray crystallography, or maybe even in chemistry. You have a unit cell, that's just this part that's going to get copied, and then you're going to tell how many rows and columns you wish to have. So that in fact is going to be rows and columns of this matrix. So there's three columns in this one. So if we say we're going to have 1, 2, 5 new columns, there are in fact 15 new values, of course, because it's replicated through like this. So I've just drawn this up and drawn in these little lines to help you see how that replication is happening. So we're going to have 3 by 5 examples of this unit cell to make this big matrix here. You can also replicate specific elements. So Replm for replicate element is going to replicate elements in the dimensions specified. So here we're going to use the keyword Replm, and then we're going to give matrix, row, and column. So that would look like this. Here is a matrix of integers, and so if we wanted to replicate specific elements, we could do it like this. So what it's going to do is it's going to basically multiply this out similarly to what we had before. But notice what it's doing is it's replicating these specific elements, right? So 50 is being replicated here, 34 is, which was over here, right, is replicated out over here, and then 96 is down there, and 59 is over here. So we talked about vectors and matrices that have things in them, but we can also have a vector or matrix that has nothing in it. So the empty vector is a vector which has no entries in it. The empty vector stores no values. It's created using the empty square brackets. So it would look like this, empty vector. So you give some name to it, equals, and then your square brackets. So here is an example of how you would define it, and it has no entries. So for example, this could be useful if you want to do something to it. It's useful if when we have looping, so you may need to say, let there be this vector, but you don't know what you're going to put in it yet. And then as you go over a loop, you would be adding content to your empty vector. So that's oftentimes what it's used for. So let's take a look at what's happening here. We've defined an empty vector, and then we wanted to add the content to the vector. So this is augmented assignment. You have the vector is equal to, and then see we have these square brackets, and it's going to be the current value of the vector plus 4. So now we're going to have 4 in there. So now what we're going to do is we're going to say the new vector is going to be equal to the current value of the vector and add another element. So here we've added 4 and 11, and now we're going to add 77 and so forth. So you can grow your vector just like this. And when we get into looping, we'll see that we're able to grow the vector as we iterate through a loop. So we can also use an empty vector to delete items from a vector. So here's a vector, and so if we do vector at position 3 equals the empty vector, this will have the effect of deleting the third entry. So this is the third entry right here. So we notice that the 5 is gone and that the length of the vector is decreased by 1. We can also decrease in a range. So here we're showing how you can do that. So we're saying vector from position 1 to 2 should be equal to the empty vector. So that will have the effect of deleting the first and second positions, these right here, which will leave us only with 7 and 9. So we talked about different sizes of vectors and matrices, but right back in the beginning when we were talking about building up matrices, I mentioned the fact that we don't need to necessarily be limited by just having two-dimensional matrices. In fact, matrices could have more dimensions than that. You could have a third dimension, or in fact, we could have abstract representation of matrices that are n-dimensional matrices. So that could be used, for example, to replicate some kind of table information, which is probably the most common use of higher order dimensional matrices. So there are ways of creating 2D matrices, which are generally going to apply for creating the 3D matrices. And you can also use layers. So we'll take a look at how to do those things. So first, let's look at constructing a 3D matrix using the layer method. So these are the steps that we're going to do. First, we're going to create two matrices of the same dimensions that are going to be the layers. Okay, so here's layer 1, and notice we're applying our reshape here. So we've made up numbers from 1 to 15 and reshaped it in a 3x5 matrix. So you see how it's numbered nicely here and how easy that was instead of typing that all out. You know, computer scientists are some of the most lazy people. Who wants to type? So here we have it done automatically with just this little command. Now we're going to make another layer. So this is sort of like having a second matrix, and then we're going to envision taking those two matrices and stacking them one on top of the other. So here we're just doing some illustration of some fancy things that we've already talked about. Layer 2 is going to be flip left, right, flip up, down of layer 1. So layer 2 now looks like this. So you see that it's numbered in this orientation. Make sure you can work out the flipping in your head to see that this is, in fact, what you would expect to get. So then what we're going to do is we're going to now make a new matrix, adding the layers together. So matrix is going to be basically putting together the different pieces, okay? So this is what we've got here. Okay, so matrix is going to have all rows, all columns, and this is going to be the first layer. So these different fields stand for the rows and columns. So we're going to make all the selections, and then we're going to call this layer 1, and we're just going to say equals layer 1. Okay, so here's the matrix. And so now what we're going to do is we're going to do the same thing to get the second layer. So you see also, again, we're going to be taking all the rows and columns, and we are going to be assigning that into the second layer, which we see right here with that 2. And it seems I just flipped slides. Okay, so now that we have those things, you see that we've joined them. So basically we're joining these together in this new matrix. And so now we have layer 1 and layer 2 of the new matrix that contains this layer 1 and this layer 2. So then what we can do is then we can check the size of the matrix, which is going to give us the dimensions out. So because these original layers were 3x5, the new matrix is also 3x5, but it has 2 layers. So we've added another dimension on to what that is. So vectors and matrices are extremely useful for a lot of reasons, one of them being that they can be arguments of functions. That means that we can pass the whole thing in to a particular function, and the function will work with the whole thing without us specifically having to iterate over it. Basically, this means that you do not have to write loops explicitly, that they are implicit for working on vectors and matrices. So an entire vector or matrix can be passed as an argument of a function. Functions will operate on each element. So here we create a vector v and take the absolute value of all elements. So here is vector, right? So we've iterated this, and then we take the absolute value of the vector. Notice that we don't have to do anything to iterate over each of the values in the vector. We just do absolute value of vector, and we see that it's done that to every single element that's in the vector automatically. We can also create a matrix and take the absolute value of all the elements. So here is a matrix, and similarly we can simply just take the absolute value of the matrix, and every single item in there has been passed through absolute value. Scalar and array operations on vectors and matrices. Scalar multiplication. So what is a scalar multiplication? Reach back into your memories and see if you can remember. Basically what this is when you're multiplying something through by some constant. So what we're going to do here is we're going to have some constant, and we want every item, every element of the vector or the matrix to be multiplied by that. So suppose we wanted to multiply by 3. So here's a vector, and suppose we want everything to be multiplied up by 3. We would simply do the new value of the vector is equal to the current vector, this one right here, times 3. That's going to be scalar multiplication. So 3 will multiply each of the items in the vector. So 3 times 3 is 9. times 7 is 21, times 2 is 6, and times 1 is 3. A similar thing will work using matrices. So here's a matrix, and then we multiply that through by 3, and we get this new one right down here. Scalar and array operations on vectors and matrices. So array operation is an operations that are performed on vectors or matrices, term by term or element by element. The two arrays must be of the same size. The elements are operated on in a pairwise fashion. And so examples of this are array addition or array subtraction. So we just talked about applying the same thing to every single element in a vector or an array. So that's like, say you want to multiply everything by 3. What we're saying in this kind is that we are talking about doing something, we're matching up the elements of one vector or array to another one. So we're going to be pairwise doing things between the two of them. So here's a vector 1 and here's a vector 2. And so if we're going to do scalar and array operations, let's say, for example, we wanted to do addition, what we're going to do is pairwise add the items in each of these. So you'll see that 2 plus 1 is 3, 3 plus 0 is 3, 4 and 3 is 7, and 5 minus 2 is 3. So that's how we arrive at this. We can also do vector subtraction, where we're going to take the difference of vector 1 minus vector 2. Again, doing those pairwise subtractions. You can also do array operations for multiplication-based operators. The multiplication-based operations are multiplication, division, and exponentiation, because they could all be written as forms of multiplication. Division, of course, is multiplication by 1 over the number you're trying to divide by, and exponentiation is, in fact, multiplying together lots of different times. So in order to specify to MATLAB this is what you want to do, we're going to use the dot operator. So you must use the dot operator, that is typing a period, before the multiplication-based operator to carry out the array-based operation. This is to tell MATLAB that we're not doing regular, but we're doing this pairwise version of it, right? Because we also have scalar multiplication, which does not involve the dot. So here is a vector and here's another vector, and to say that we want to do this pairwise operation, we're going to use the dot star. And so now we'll have the effect that we're going to multiply the elements together. Here is division. So what we're going to do in this is we're going to divide vector 2 by vector 1 pairwise, right? So here's our vectors and we're going to do that division. And we can also do exponentiation. As we mentioned, the dot operator is required. Here's the dot operator here for multiplication. Here's the dot operation for division. And here is the dot operation for exponentiation. That brings us to logical vectors. So logical operators are ones that return a value of true or false. Logical vectors use relational expressions that result in true or false values. For example, we can do pairwise comparisons to determine whether each element is greater than or less than or so forth of some number. This will result in a vector of the same length containing the logical true or false values. Now, MATLAB is going to give those answers in a numerical format. 0 will be false and 1 will be true. So taking a look over here, we have a matrix, and let me just move this out of the way. So here we have a matrix, and then we're going to ask the question, is the item greater than 3? So this is a variable that's going to collect the true and false answers about this question. So we're going to say, are the items, the elements of matrix M greater than 3, true or false? So what we're going to get back is a logical array, and it even tells you that it's logical, and it provides the dimensions here. And so taking a look at this, we've gone from 1 to 3 and 4 to 6. So 1, 2, and 3 are in fact not greater than 3. So we get the zeros there for the false. And then we get the 1 values down here for true. Now we can ask some other questions. We can ask, is it less than 3? And so we see that 1 and 2, which are represented by these positions right here, are going to be true, whereas all the other elements in the matrix are going to be false. We're on logical vectors. The resultant logical array can be used for further numerical operations. The type of vector is logical rather than double. Remember, that has to do with our precision. So we're typically working in double precision. So we're not doing that here when we're doing true and false. We could store 1s and 0s with lots of decimal places, but that would really just be a waste of space. Logical indexing, the logical vector can be considered as an index to the original matrix. Remember, we talked about indexing and how we could have an indexing matrix to pull out particular positions, thinking about that like pulling out particular information from a spreadsheet. So we can also use this to select out cases that are true, for example, or select out cases that are false. So maybe we want to have some data set and we always want to screen it for some true or false conditions. Then this is the way that we can do it. The sum function can be used to see how many elements of a vector were true. So sum, as you might guess, is going to sum up the elements of a vector to find out what it was. And so if the choices are only 1s and 0s, if we apply sum to a logical vector or a logical array that we get out, then what we can do is find out how many things had 1s in it, which will be the number of true cases. It will sum up any vector that you give it, and it will operate, do column-wise sums for matrices. So here are some examples of what we can do here, right? So here is a vector, and we're applying a condition here. So we're going to check to see if the items in the vector are greater than 1. And so 2 and 3 are going to be greater than 1, whereas 1 will be not. So that's 0, 0, 1, 1. And then what we're going to do is we're going to apply the sum to this resultant vector that we got, the logical operator result. And so we get 2. So we know that there were 2 cases that were true. Now we can do a similar thing for the array, which we're showing over here. Again, we'll test for whether or not the elements are greater than 3. So we get out a 2 by 3 logical array to report that answer. And then what we can do is we can take the sum of that, and what it's going to do is it's going to give us the column-wise totals for whether it was true. So we have one entry in each column that was true, so it looks like this. We can create a uniform logical vector of a specified size. So suppose we want to create a vector that's 3 by 3 that's going to contain all falses. So this is what it would look like. So similar to what we've seen before when we created the 0s or 1s, what we do is we pass in a single dimension. So here we get a logical array that's full of 3 zeros. Now, recall that this is distinct from the zeros vector, which actually contains not the logical value of 0, but the float value of 0. Okay, so it's important that you understand that those are different. This is a true/false value, whereas the other one was a number. Okay, here we can do the same thing with true, and just like we saw before, if we pass in two numbers in here, this is going to produce an array of the dimension specified. So this will be a 1 by 5 logical array being shown here. That brings us to matrix multiplication, the dot product and cross product, which your book largely groups as matrix multiplication topics. These are often all taught together in probably a vectors and matrices course, and you would probably also encounter this in linear algebra. Again, if you're not an expert or you've never done any of these matrix multiplication procedures before, the goal of this class isn't that you necessarily learn how to calculate these things by hand. You should be familiar with what's happening here, but I'm not interested in asking you to calculate these things by hand. Should you learn how to do it? I mean, I think it's a really great thing to know how to do, and it's advisable for you to take these classes and to learn how to do these things. But our purpose in MATLAB is just to be able to use them. So as long as you understand when to use them and how to use them, That's sufficient for the goals for this class. You want to do more, you never did vectors and matrices before and you want to learn, go right ahead. You know, I think this is a great opportunity to learn that and you're going to get all the more out of this class. But if that's not your thing or you don't have time to do it right now, you can get to it when you get to it. So I am going to show you the mathematical operations, but I'm going to talk through them in a rather cursory way. If you do want to learn them, definitely move into just looking into a vectors and matrices textbook of any kind. I'm sure you can see how to do it there. Also, there are many resources on the web on how to do this. All right, so this is how matrix multiplication is done. And this may seem very unusual because it is a kind of an interesting procedure. It turns out that this kind of matrix multiplication does have a lot of applications in physics. So it may not seem like a representative thing to do, but you have to just kind of trust me on this if you haven't seen it before, that this is a meaningful thing to do. So what we're going to do here is perform the matrix multiplication. We're going to do column by row. So here we have a column, right? So we have, this is a 2 by 3, 3 by 2 matrix, and then we have a column vector right here. And so what we're going to do is we're going to perform this kind of strange operation here. So what we're going to do is we're going to take this, so this column goes by this row. So all of the items in this column get multiplied by all of the items in the same row. So this is column 1, this is row 1. And we're going to add them all up. So we do A times G, and then we're going to, so you see A times G, and then it's going to be plus B times H. So it's a way of saying multiply each of these times their respective numbers, if you will. All right, so we do A times G plus B times H, and then we're going to do C, that's the second one, times G. All right, so this is, because this is still the first column, we multiply it still by the first row, but we only have one choice, so it's times G, right? So this one, they're going to match up like that. And then E, so it's going to be E times G because this is still the first column. And then we pick the item from the first row. So that's how we get this part over here. And then this filling out this second section over here is going to be the second row, this second column times the second row. So here is a B will be times H, and then D being still in the second column will be multiplied by the second row H, and so forth. So then we have F times H as well. And then we have to do this summation procedure over here. So once we've figured out what these items are, then we multiply them up. We multiply them up and do the addition to get out what the answer is going to be. So from this, we see that there are going to be some restrictions on the size of what the matrices can be. So a 3 by 2 matrix can be multiplied with a 2 by 1 because you see that the 2's match because the number of columns has to equal to the number of rows in order for this matrix multiplication to work. And then the matrix that you're going to get out is the resulting matrix is going to be these outer dimensions that are kind of like left over. It's going to be a 3 by 1 matrix in this case here. So I just thought I would give you a couple more examples to show you what it would look like. So here is another example where they're starting to fill this out. So we have, again, the multiplication occurring over here. Here's another example of the matrix multiplication worked out for you to give the complete solution. So matrix multiplication is kind of complicated and it's going to take a long time to work it out by hand. So isn't it great that we have the star operator for matrix multiplication in MATLAB? Thank goodness, because otherwise we'd have to be doing this all by hand. So this is what that would look like. Here we have a matrix and here we have another matrix over here, and we just put in the star operator and look at that. There's the answer. How convenient. So in MATLAB, the star operator will perform the matrix multiplication. So here we're showing what the matrices are, which is illustrated right here. We have a matrix A, and then we have a matrix B. And so then C is simply going to be equal to A times B. You can go through and verify that the dimensions are going to work out so that everything will be able to be multiplied. Vector multiplication. So it's going to work the same provided the dimensions are correct. So here's a column vector and here's a row vector. So note that the row is 1 by 4 and C is 4 by 1. So then when we multiply them up, we will be able to get a scalar. So here we're going to do each one element by element, right? So there is only one row and there is only one column. So first element in here, right? So it's going to be 6 times 5 plus 2 times 3 plus 3 times 7 plus 4 times 1. And we add all this up and we get 61. And here in another case, we're going to look at some alternate dimensions, right? So in this case, being the column vector times the row vector, the answer is going to be quite different. So it's important to recognize the fact that the order matters, and it will be important that you put them in the correct order to get out what it is you are in fact looking for. We also have this scalar or dot product of two vectors. So this has a representation in both geometry and in algebra. So your book is defaulting to the algebraic representation. I personally prefer the geometric representation of it. So I've just summarized both of those for you here on this slide. So the scalar product or the dot product between two vectors P and Q is going to be defined as P dot Q or PQ cosine theta, which is going to give you the scalar result. So the scalar product math properties are commutative, distributive, and not associative. The alternate representation given by your book is given by this formula right down here, A1B1 plus A2B2 plus A3B3 and so forth, right? So basically it is a sum. There are two different ways you can calculate the dot product in MATLAB. So the first method is you're going to define two vectors and then you would use matrix multiplication, which is the star operator. You would multiply the first vector times the transpose of the second vector. So basically you're doing a row vector versus a column vector, which is useful to think about in terms of that algebraic representation. The other method is you're going to define two vectors and then you're going to use the dot operator. So you just put in the word dot right here, which is an operator, and then you're going to have vector 1 and vector 2. So either way you can do it, they both work out to give you the answer for the dot product. Also, we have the cross product. So the cross product is resulting when you're doing this cross product operation to give a third vector. This is the mathematical representation of how the cross product is calculated. So oftentimes we think about this as having the I, J, and K unit vectors going along the axes, and then two other vectors which are having components in each of these axes. So if you're not really familiar with this, that's not too much of a problem for the sake of this class, although these are, again, definitely useful things that you want to be familiar with if you're going on in higher mathematics. The I, J, and K vectors are basically the vector of unit size 1 in each of the X, Y, and Z coordinates in the three-dimensional coordinate plane or coordinate space. And so then when you multiply them by these scalars that are associated with them, what that's saying is that that will give you the size of a vector resolved by components into each of the axes. So you can take vectors and resolve them into their I, J, and K components if you do this kind of a class. Again, that's a typical exercise that you'll do is resolving vectors into the unit vectors and representing in this particular form. So this is useful when we want to do things like figure out the resultant vector when we do A cross B. And so what is being shown here is some vector A and some other vector B. And when we do the cross product of these two vectors, we're going to get this resultant vector up here. It's sort of like the vector in between them. It's kind of like an averaging process, but in three-dimensional space, including direction. You may have also encountered this in a different form, which is using this cross product where so when you're doing one times the other, whichever element you're on, you're going to block out that element inside the matrix by which you're multiplying it by, and so it follows this pattern here. So A2B3 minus A3B2, right? So it's kind of complicated, but you see that in each one of these items here, there's going to be a missing element, right? So when you're in the first position here, you're going to be missing all the sub 1s. In this one, you're missing all the sub 2s, and in this one, you're missing all the sub 3s. So you may have worked through that. Anyways, this is what the cross product is, and MATLAB will definitely simplify your life if you need to calculate cross products, because it will calculate them for you. This is going to be an example of calculating the cross product. So suppose you want to calculate the cross product between these two vectors. So here is an example of how to set this up. Just set it up with the unit vectors, and so I, j, k are put up here, and here filling in the vector values, and the cross product is being computed, which will give you the corresponding components for the I, j, and k parts, and this is the solution to this problem when you multiply those numbers up. Okay, we can also calculate the cross product in MATLAB. So here's a vector 1 and here's a second vector, and so all we need to do is just use the cross operator. So you do cross of vector 1, vector 2, and we will get the answer. All right, so then that brings us to our summary and conclusions for today's lecture. We talked about vectors and matrices today. We talked about basically how to create them and some of the special vectors and matrices, the zeros and ones that we could have, their dimensionality, and the relationship between scalars, vectors, matrices, and multidimensional matrices. Vectors and matrices can be arguments of functions, which makes the processing of them much simplified. Scalar and array operations on vectors and matrices are possible, and we can also work with logical vectors, that is, ones that give us true and false values. Finally, we talked about matrix multiplication procedures, which include actual matrix multiplication, the dot product, and the cross product. All right, then with that, looking ahead, what you should be working on is the practice problems throughout Chapter 2. That will be your lab exercises for this week. You can kindly post those by Wednesday at 10 p.m., which is when your lab would have ended. Work on that for about an hour or so and post whatever you've gotten done. If you're having difficulty working with them, you should plan to have an online chat with either me or our course assistant. The homework for this week is going to be to complete any 10 problems from Chapter 2 exercises and post to Moodle. Please get those in by next Wednesday at 9 a.m., which is the time when I'm going to be grading your homework. Certainly feel free to stop by and visit me on any of the Zoom meetings, either in our class time or any of the office hours. The Zoom links are found on Moodle. All right, so I hope you had a great time learning about vectors and matrices, and this is giving you some great insight that will get you started on learning MATLAB. Till next time, bye-bye. Mm-hmm.